Yeah, thanks for the invitation. Happy to be here. And be here virtually, I guess. Okay. Um, great. So yeah, today we're going to talk about, I guess the title is a general Heegaard Floer surgery formula. And what I'm going to talk about is just some of my work related to the surgery formulas in Heegaard Floer theory and kind of extensions and refinements of these theories. So I'll remind you kind of that they spent a lot of time computing Heegaard Floer homology of surgeries. Right, so they're studying this, right, so if you have a three-manifold Y, they study this, oops, sorry, remember how to use this. So if they have a three-manifold Y, they're going to consider this group or this module, let's say CF minus of Y. And this is an F adjoint U module. Or chain complex over F adjoint U. For our purposes, just kind of as it relates to the surgery formula, it sort of is more natural to actually consider this with power series coefficients. It doesn't really change the flavor of anything. And so, kind of one of the earliest stories in the theory is, if you have a Dane surgery, if you have a knot, let's say K and S3, how do you compute the Floer homology of Dane surgery, let's say N framed or P over Q framed Dane surgery on K. So that was, that's a very natural thing to do from the low dimensional topology perspective. It's something that we'd really like to do. And so they gave this very beautiful formula for doing this. And it's called the mapping cone formula. I think, it's something that a lot of people in the field are familiar with. And so what they showed is that they showed that CF minus of Dane surgery on the knot is a mapping cone, or it's a mapping cone chain complex between two objects. And they wrote V plus HN is the maps in the mapping cone. Maybe I'll write it this way. So they wrote it going a complex A. It's the mapping cone of from between two chain complexes A and B of a sum of two maps V plus H sub n. Okay, so they've, but the thing that's important is that these complexes A and B are more computable typically than actually the Dane surgery, the CF minus of the Dane surgery. So typically A is sort of written as a direct sum over Z of these A sub S complexes, and B is sort of written as a direct sum over these B sub S complexes, which still haven't told you what anything is. And this is a pretty practical way to work with it, but it sort of is not the most conceptual way to think about it. And really, we should really think of it instead as sort of this. If you kind of stare at this for a little bit, and you ponder what this actually is, you can see that this is actually sort of the knot Floer complex of the knot K. And there's a lot of things that you can write CFK for. And what this is it's really sort of the free module over a two-variable polynomial ring. So I'm going to write WZ for these two variables. Sometimes in the literature, you might be familiar with U and V, but this kind of gets a little bit messy to write by hand. So I'm going to write W and Z for the two variables. So the kind of A complex in the mapping cone formula turns out to actually just be sort of the knot Floer complex viewed as, in terms as this sort of finitely generated chain complex over this two-variable polynomial ring. So, as an example, CFK, if you have maybe if you're not super familiar with these gadgets, CFK of the trefoil, for example, has three generators and two differentials. And the differential looks like this. So each dot represents a copy of the ground ring. So each dot is a copy of F adjoint WC. And the differential sort of takes this very simple staircase complex. And so in general, this is more computable than, in general, it's easier to compute the knot Floer homology of the knot than it is to compute the Floer homology of its Dane surgery. And this complex B is equal to, well, actually, each of these B sub S complexes basically turn out to be a copy of F adjoin U. Oh, I guess I haven't said it, but we view this not Floer complex CFK of K, CFK of K as an F adjoin U module where U acts by the product WZ. And so this kind of, you multiply both of the variables together, and this gives you sort of a U action on the whole mapping cone. Right. So this is an isomorphism. Maybe I'll say that this is an isomorphism of F adjoin U modules. F adjoin U, or chain complexes over F adjoin U. Okay, and so, right. Okay, so there's a lot of extensions of this formula. So there's many extensions of this formula. There's many extensions, and I'll list a few. So, there's probably, well, one very important extension is Manolescu and Ojva. Manolescu and Ojva. It defined a link, constructed a link surgery complex. So there's this link surgery complex. And this is a chain complex which computes Dane surgery on a link, link surgery complex, link in S3. So this is for if I have a link in S3, there's some chain complex C lambda L, and this computes CF minus of the Dane surgery of lambda surgery on L. So that in one direction, we kind of have a generalization which computes Dane surgery on links. So we add, knots with many components, I guess. And then in another direction, there's a formula of Eftekari, Hedden and Levine, which what this does is it computes it doesn't compute CF minus, it computes the knot Floer homology of the dual knot in the Dane surgery. So it computes, so maybe I'll write it this way. The input is sort of a knot K in S3, and the output is not CF minus, but CFK of the Dane surgery, the meridional knot in the Dane surgery. So if I have my knot K here, let's do it. If I have my knot here, what this is going to compute is sort of the knot Floer homology of this meridian inside of the Dane surgery. So this little meridian that's mu there. And then there's some generalizations of this by, there's generalizations by Hugo Joe and also Lin Trong. Maybe they're independent, but they're kind of building, Joe's work kind of builds off of Lin's work, Joe's work builds off of Trong's work, and this computes, CFK cables of the dual knot, not all cables, but many cables of the dual knot. And this has had some nice topological applications. And there's a number of other generalizations. Maybe I'll just say that some of Hedden's earlier work on cables and satellite operations, is actually, even though on the face of it is not quite of the flavor on the face of it is not quite fitting into this package. Some of the proofs used in there are sort of mirroring the proofs that Ojvath and Szabo gave, and Manolescu, Ojvath, and kind of in this they kind of all kind of fit into this one package of they kind of fit into this one packet, style of invariant, and they all kind of feel like they're using the building off of the same theory, or sub-theory of Heegaard Floer theory. And so the most natural question is just, can we unify these theories? Can we unify all of these theories? Can we have some sort of package where, like, it lets us, that kind of encodes the surgery formulas and also lets us do each one of these kind of fitting into a single sort of umbrella, which explains how each of these things arise. Because on the face of it, each of these results kind of just is independent. I mean, they all kind of use similar techniques, but they're not fitting into, a single unified package, and their relation is not necessarily clear on the face of it. Sometimes, the authors will just use ad hoc arguments to sort of figure something out, and it's clear there's this very deep theory there, but like it's not entirely clear how to relate the link surgery formula to, say, the Eftekari, Headed, and Levine formula. Great. Are there any questions so far? Okay, and so maybe the goal is just to describe sort of a general proof of this. So maybe the goal of today's lecture, the goal of today is to just describe, on the face of it, it doesn't appear to sort of unify all of these theories, but it gives, the goal is to give maybe a flexible framework which encodes all of these results. And I'm not going to be able to explain how we can derive each of them from a single source, but like the goal is maybe actually, let's maybe give a more modest goal, is these invariants. The goal, and actually let's just describe a general surgery formula for knots in 3 manifolds. So maybe for today, okay, just for any knot in any 3 manifold, for knots in 3 manifolds, and think about what shape this would take, and what this would look like. Note that I guess as a remark, kind of to explain why this is useful, is that Ojvath and Szabo's proof generalizes to say rational, it generalizes to the kind of the farthest you can push their proof is to rationally null homologous knots. But neither the proof nor even the statement of the surgery formula are going to work for homologically essential knots, for example. And so just as a basic case, you kind of realize that just their formula doesn't actually kind of work in full generality. It doesn't kind of give, a Dane surgery formula that works for any knot in any 3 manifold. And also, for example, it wouldn't work to give a Dane surgery formula for a knot in a 3 manifold with boundary, for example. Like, it's very specific to closed 3 manifolds, and specifically rationally null homologous knots is really the farthest you can push it. But kind of the thing that we're going to describe today, or we're going to attempt to describe today, just kind of works in generality. It works kind of in all of the Floer theories for any knot. It can be homologically essential. It works sort of in this sutured Floer homology world. And so that's kind of the goal of this, is to just give a very flexible framework that's also more user-friendly and kind of avoid some of the technical hurdles that the kind of prior techniques required. But not, maybe I'll finish the sentence here and then we'll move on. Not homologically essential knots. And not sutured manifolds, I'll put it that way, not sutured. Oops, I'll write. Not sutured manifolds. Okay, and so we're just going to kind of describe what this would look like. Okay. And so what we're going to begin by doing is just sort of, we're actually going to kind of enter just some symplectic geometry, or think about symplectic geometry. So we're first going to recall how the surgery formula is proven. and actually, before we prove, before we're not going to prove it, but like before we actually do the surgery formula, let's just recall how the exact triangle is proven. And kind of, we're not going to go through the proof, but just like, what does the exact triangle actually mean? So the exact triangle, by which I mean the surgery exact triangle. And sort of, let's think about the most basic version of this. So what this actually, so the most elegant sort of version of this, right, or maybe I'll state the exact triangle. It says that there's an exact triangle on the Floer groups if I have a knot, let's say K, inside of a three-manifold Y. What it says is that I have this sort of exact sequence, HF minus of, let's say, Y0 on K. And maybe actually, instead of 0, I'll write lambda for a longitude. So any sort of longitudinal surgery. And then I'll go to HF minus of Y lambda plus 1 of K, and then HF minus of Y, just HF minus of Y. That's sort of infinity surgery, I guess. So this is the exact triangle, and this is sort of one of the key tools in proving the mapping cone formula. I mean, the mapping cone formula is, for example, the mapping cone formula is basically just an exact triangle. In homological algebra, mapping cone formula is sort of equivalent to a long exact sequence. And the, Ostwald and Szabo's original proof of the mapping cone formula was to use sort of a generalization of this sort of standard surgery exact triangle. And so what I want to do is I want to just describe, how to actually prove this, or kind of one perspective on it, which is very nice. And so you can actually reduce this surgery exact triangle to just a statement about 3 Lagrangians in the torus. I'll write it this way. You can reduce, you can sort of using just basic properties of Heegaard Floer homology, you can reduce the exact triangle. The exact triangle to a statement about knots in the torus. Oh, sorry, not knots, Lagrangians in the torus. Lagrangians is what I meant to say. Lagrangians in the torus. Okay, so we're gonna, oops, I've destroyed something. Okay, we're going to look at this torus here, and right. And so I'm going to draw three Lagrangians here. So I have an, let's see, let's do green someplace. So I have 3 Lagrangians. And I'm going to label these. So maybe this one I will call gamma infinity, and I will call this one gamma lambda, and this one will be gamma lambda plus 1. Okay, and I'm sort of running out of room here, so I'm going to just copy this and go to the next page. Copy. Paste. Okay. Okay, so we have these 3 Lagrangians, and so we can consider these Lagrangians, we can think of them as objects in the Fukaya category. So gamma infinity, gamma lambda, and gamma lambda plus 1 are objects in the Fukaya category. These are objects in the Fukaya category. I'll write F of T2, and I probably want to add a base point, so let's add a base point there. So this is just some base point necessary to work with, necessary to do Heegaard Floer homology, or necessary in the framework of Heegaard Floer homology. So this is the Fukaya category. So in the Fukaya category, objects are Lagrangians, and morphisms are Floer chains, so intersection points. Okay, right. So in the Fukaya category, the objects are Lagrangians and the morphisms are intersection points. And it turns out what you can do is you can sort of enlarge the Fukaya category. And so in homological algebra, you want to be able to build the mapping cone of a chain map. And so in the Fukaya category, like there isn't really a natural notion of a mapping cone, because if I take, then that kind of requires two Lagrangians and a morphism between them. But what you can do is you can sort of enlarge the Fukaya category, and you form what's called the category of twisted complexes in the Fukaya category. So you can enlarge the Fukaya category. And so what you get is you get a category called the category of twisted complexes in the Fukaya category. And basically, these are just chain complexes of Lagrangians. Chain complexes of Lagrangians is kind of just all you have to think about it. And it sort of is the framework that you can do homological algebra within the Fukaya category. And for most purposes of computing Floer complexes and stuff, this is actually a little bit more natural category than just the Fukaya category itself. And so within this category, we can form twisted complexes because they're just kind of on the face of it. You take two Lagrangians and you take a morphism between them. And the exact triangle has this very nice statement in the category of twisted complexes, which is actually just that gamma infinity is homotopic to the mapping cone of, well, there's a unique morphism from, there's this unique morphism, which I'll just kind of label here as theta, between gamma lambda and gamma lambda plus 1. And it's this gamma infinity turns out to be the mapping cone of this unique morphism from gamma lambda to gamma lambda plus 1. And kind of from this, from this homotopy equivalence, basically you can just very quickly derive the surgery exact triangle on Floer homology groups. It all kind of boils down to just this fairly simple statement about three Lagrangians in the torus. So this is the original surgery exact triangle. Are there any questions about this? So Oshvath and Szabo used an extension of this surgery exact triangle to prove, maybe I'll go back before. Oshvath and Szabo used an extension of this surgery exact triangle and some other techniques to prove the mapping cone formula for Dane surgery. But they didn't quite, one thing that was left is that Oshvath and Szabo, and I mean, none of the subsequent authors never proved an exact analog, never proved an exact analog of this for the Dane surgery formula, exact analog of this, isomorphism, of this sort of isomorphism, which was, of the long exact sequence, which was kind of, oh, sorry, not beta, let's use gamma. They never proved an exact analog of this kind of isomorphism for the Dane surgery mapping cone formula that we talked about in the introduction. There were sort of approximations to this, but they never proved one on the nose. And kind of the challenge is that the limitations of the mapping cone formula for not being, in S3, or for being, I guess, null homologous, all of these limitations come because they really only sort of proved an approximation. The Fukaya category fact that they proved was really only an approximation to the actual surgery mapping cone formula. And they never actually proved on the nose the actual mapping cone formula just in terms of the Fukaya category. And
Can
so
you say, sorry, Ian,
yeah.
can you say what the difference is and why it's an approximation? Because I thought their proof basically did say that in the Fukaya category, these were the same.
Right. Okay, so that's a good question. So what they actually proved, sure, I was hoping to avoid it, but it's good. So what they actually proved is that they proved that the they proved that, so they did prove a statement about knots, sorry, Lagrangians in the torus. And the statement,
Oh, did they prove the statement that when you apply the Yoneda embedding, then these are
no, it's
oh.
not quite that. So they showed that if let's say, let me try this. So B lambda, let's try, this would be B lambda. Then they showed, let's say this will be, I'll call this B infinity. And what they showed is that if you sort of wind sufficiently many times, so they showed B lambda plus n. Well, they showed that there's an isomorphism. B lambda is isomorphic in the Fukaya category to a cone B lambda plus n to B infinity. So they have these three Lagrangians, but instead of just incrementing the meridian by one, they increment it many times, and n can be anything here. Usually you think of n as being very, very big. And this Lagrangian is given a local system. And we'll talk a little bit more about local systems in a minute, but for the purposes of the moment, it doesn't really matter what local system it is. They just give it some local system. And so concretely, what this amounts to showing on the level of the exact triangle is that there's a long exact sequence, or maybe I'll write it. What this actually shows is that gives you an isomorphism HF minus of the lambda surgery of your knot is isomorphic to the cone of some map, which I guess you know it's some sort of cobordism map from HF minus of y lambda plus n of k to HF minus of some sort of twisted version of HF minus of y for some cobordism map. But these aren't sort of the terms that appear in, maybe instead of y, I'll actually just put in S3. I think it'll be so that we can kind of see a little better. So, but I mean, so this is sort of what they prove, but this you'll observe is not quite the mapping cone formula. And you can see here, so the next ingredient is they use a large surgery formula. So they use a large surgery formula, which says that if n is very, very big, then HF minus of S3 lambda plus n of k is, say, isomorphic to, let me rewrite it this way, a subcomplex of the knot Floer complex, CFK of k. So there's kind of two ingredients here that they used. And then this guy is sort of a direct sum of not infinitely many copies of HF minus of S3, but this turns out to be I think n or 2n or something like that. Yeah, probably n copies of it. N copies of HF minus. So it's kind of an approximation. It's not actually equal to the mapping cone formula. And so there's one ingredient here that you need, which is this large surgery formula, for example. And in principle, one might be able to generalize that to one might be able to make, okay, so a large surgery, it requires, a Seifert framing to be precise. And so, in a sense, that doesn't work for homologically essential knots. I mean, without some extra work. And the thing is, this ice, what they do is they take this complex and they show this is homotopy equivalent to the mapping cone formula. But it's not equal to the mapping cone formula, and it kind of takes a lot of work to show that. And so if you when you're proving extensions of these formulas, it kind of gives you a big headache to do this over and over, and kind of like the extensions, every time you extend it, it gets more and more complicated. And so kind of the thing is, we don't want to use this technique if we don't have to. We want to kind of come up with a new technique, which just on the nose gives us sort of the exact, it just gives us the mapping cone formula, just sort of on the nose, and lets us see exactly what's going on. Are there any other questions? Okay. So my goal is just to state this other version of it, and then we'll we might be able to compute it for like, I don't know, the unknot in S3, or we might be able to use this description for the unknot to see how this works. Okay, so what I want to do, so I'm just gonna, okay, so this is how this works. So I'm just gonna try to state it. So here's basically it's sort of a modest goal. We're just gonna try to state this. It's a new description of the mapping cone formula. That's kind of the goal for today. Okay, so what I'm going to do is I'm going to consider 3 Lagrangians in the torus. Just as before, but they're going to be different ones. And they're not going to be any of the ones that appeared before. I'm going to start with sort of what I'm going to consider as the longitude. So I'm going to call this beta lambda. That'll be the longitude. And we'll start with one that'll be the meridian, and I'll call this beta 0. And then I'm going to add in a third one, which is going to be isotopic to this beta 0, but it'll be sort of wound once. Let's see. Oh, maybe I want to move this guy up. So I'm going to consider these. Oh, maybe I should use a different color here. Let's do this. Okay. Let's do a different blue here. Okay, so this one will be beta 0, and this one will be beta 1. And so on this diagram, I'm just going to put 2 base points. So this will be, I'll put, oh no, that's not at all what I wanted. Okay, there we go. So I'm going to put a W base point here, and I'll put a Z base point here. Okay, and so I want to consider, you'll notice that there sort of are 4, there's sort of 4 intersection points. And really, if you think about this, this is a diagram for, if you kind of, let's see, what do I want to say here? You can think of this as like CFK if you want, or maybe I'll write it this way. So T2 beta 0, beta 1, WZ is the diagram for like a knot. It's maybe an S1 times. So it's a Heegaard knot diagram for S1 times a point inside of S1 times S2. Okay, and there's 2 intersection points I want to consider here. So I'm going to call this one theta sigma plus, and this one will be theta tau plus. And it turns out to write down this exact triangle, I need a little bit of extra information. And so what I need to do is I also need to add, well, I need to add a knot shadow here. So what this means is it's kind of a, it's just an embedded curve on the surface that sort of represents this knot. So it represents maybe this knot, this S1 times a point in S1 times S2, for example. And so basically it's just going to go through the betas and avoid the alphas. So let's draw it like this. Okay, so I need to add a knot shadow. That's just, it's not a Lagrangian, it's just some curve on the surface. And now I want to give, we're going to define what are called local systems. I'm going to define local systems of F adjoin U modules on beta 0 and beta 1. Now a local system on a Lagrangian, so right, a local system kind of abstractly is, you can think of it as a representation of the fundamental groupoid. Representation, this is kind of an abstract way to describe it, of the fundamental groupoid on some space, let's say of you know, a local system, let's say on a Lagrangian L, on L is a representation of the fundamental group weight of L on some space. I'm going to call it E, right? So that means that to given like a path, but a path between 2 points, I get some endomorphism of L. And really, we're really only interested in like going around a loop around these Lagrangians. Okay, and so there's sort of beta 0. I'm going to give it this. I'm going to call it. Gonna give it this space E0, which will be just F adjoin WZ. And beta 1, I'm going to sort of give it this, the sort of representation space is going to be this space F adjoin UT T inverse. Okay, and so, Floer homology sort of naturally extends to the framework of having these local systems. So if I have, say, two Lagrangians L1 and L1 with local system E1 and L2 with local system E2, right? So this is some vector space, right? So local system will have a vector space or a module. Right, if I take a pair of such things, of such Lagrangians decorated with these spaces, I can naturally describe their Floer homology. And what this is generated by pairs where X, let's say pairs X, F, where X is in the intersection of L1 and L2, just like in the normal Floer homology, and F is now just some map. It's just a linear map from E1 to E2. So I'll continue this on the next page. Okay, so this is Floer homology with local systems. Okay, and so there's a natural way to define the Floer differential on such things. So if I have, so let's say I have, some holomorphic disk, we're going to count holomorphic disks, and let's say kind of the input. So let's do del of XF. So let's say XF is the kind of input to the differential, counting Floer disks. And let's say I have some Y, this disk goes from this intersection point X to Y, and the output morphism G is going to be, what you're going to do is you're going to compose, basically what you do is you just go sort of counterclockwise, composing maps along the boundary of the disk to get G. So what we do is we say G is going to be the composition first of the, I'm just going to write it, the monodromy map of the local system, right? I have 2 points on, let's see, this would be L1 and L2. I have 2 points, X and Y on L1, and I have a path from them specified by the disk. And so I first do the monodromy map for L1 along this path. I compose it with F, and then I compose with the monodromy map along L2. So this would be the monodromy map. These are sort of the monodromy maps.
Do you mean to be going counterclockwise?
Do I mean to be going, I guess we're going clockwise. I want to do L1 first, I guess. I think is the natural order.
But from Y to X, or?
From Y to X. Yes, we go from Y to X. Yeah, so we kind of go from along L1 from Y to X, and then we compose with F, and then we go back to Y along L2. If you play around with it, it's sort of clearly the right thing. You have to kind of ponder it for a little bit, but it's like the only sort of thing you could possibly do. Other than like you could go in the, I mean, you could sort of define things contravariantly as well, but like, so really the only sort of possible thing to do. And so this is like this is a really simple frame. I mean, it's really natural framework. And so basically this is the framework we want to use, is these sort of Floer homologies with local systems, and I want to go back to these Lagrangians. So let me copy this again, and I'm going to tell you what these local systems were. So copy. Let's just copy this, and so okay, so I have these local systems. The space for beta 0 is F adjoin WZ, kind of very basically, we're going to get the not Floer homology. The space for beta 1, the representation space, is F adjoin UT T inverse. And I need to tell you what the monodromy map is. And so basically, we're going to look at this not shadow, and we're just going to count the number. So if we have a disk or a polygon, we're just going to sort of the monodromy map, it's like we have an arc on the Lagrangian, and we're just going to count the number of times that we pass along the boundary these two intersection points, and that'll give us the monodromy map. So let's say, and I'll tell you what this is going to be. This is going to be the monodromy map, rho 0, is, let's say, of a path gamma. Let's call this a path along beta 0, is just going to be sort of, it's going to be Z to the intersection number of gamma with this, I'm going to call this the shadow K. So this kind of, K is the shadow. Oh, and I guess maybe times the identity. Okay, so maybe times the identity, let's see. So you'll kind of notice it looks a little funny and maybe even a little suspicious. So for example, you'll note that like Z to the -1 times the identity is not like a genuine endomorphism or automorphism of E0. Like, but that's, certainly you could have Z to the -1 if the intersection number is negative. But it, it sort of turns out that it sort of, I'll show you in a minute, like sort of, the real representation space, you should really have negative powers of Z allowed here. But okay, so abusing notation, we're just going to say that E0 is just the space with positive powers, and that turns out to be what is sort of important for our purposes. But to actually define this as a local system, you, in a sort of genuine sense, you would need negative powers of Z. But it turns out it won't be sort of important for sort of basic reasons. As we'll see. And so for beta 1, what I'm going to define a monodromy map, which is going to be very similar, but it's just going to be, we're just going to multiply by T times the intersection number of a path gamma with K times the identity. And this one, we don't have to worry so much because T can be negative here, so we don't have to worry about that. And so basically, we're just drawing, we take the class of our polygons and we just sort of count the number of times they, cross this point in either direction, and we count it with sign, and that gives us the power. Right, so we also had these sort of Floer morphisms, right? If we look in 1 or 2 slides ago, we thought morphisms here, CF from one Lagrangian to the other, they're pairs intersection points with a map. And it turns out there's 2 sort of canonically specified maps. There's 2 really important maps from this E0 space to this E1 space, E0 to E1. And they're gotten as follows. They're just F adjoin U module maps, but they're just given by the following formula. So Wi Z to the J is just going to be U to the I T to the J minus I, and phi tau of W I Z to the J is going to be equal to U to the sorry, this is a J. It'll be U to the J T to the J minus I. Okay, and so I'm going to use these sort of linear maps, and I'm going to construct 2 very special cycles or morphisms from beta 0 to beta 1. So I'm going to construct these 2 morphisms, theta sigma plus, and I'm just going to equip it with this linear map sigma, and also theta tau plus, right? We have these, I'm labeling these two intersection points here. And these both kind of go from beta 0 equipped with this local system E0 to beta 1 equipped with this local system E1. Okay, so I can sort of form them. And I guess we can maybe just look at this in a second. One thing is you can realize that these are both cycles. These are both cycles. Oh, sorry, I didn't tell you how to count curves. There's one more sort of subtlety in how curves are counted. And so what we want to do is we want to count curves, right? I haven't quite told you exactly how holomorphic curves are counted, but what we're going to do is we're going to count. So let's look at, in particular, let's look at beta 0, E0, beta 1, E1. So we're going to count polygons as follows. It looks a little weird. So we are going to count, right, we're going to count disks with one more sort of, let's say, so let me just tell you how del xf is counted. So this is going to be, we're going to sum over y. Or let's just say, if I have a disk from x to y, then what are we going to do? Well, we're just going to count. So let's say this is beta 0 and this is beta 1. I'm just going to count the intersections with k and I'll mark them here. And I'll count the intersections on both of them. So let's say this is x comma f. And then I also need to keep track of sort of where it intersects, where it covers the base point. And I have to sort of pick there's some asymmetry in here in that the monodromy for this local system, we use just powers of z here. And so what I want to do is on the inside, I want to count the multiplicity at w. And so in the end, what we want to do is, I guess I'm running out of time. So kind of, we're going to define G to be the composition of F composed with Z to the intersection of, the beta 0 boundary. In the end, what this works out to is kind of, we're going to compose with Z to the intersection with the beta 0 boundary and K, and then we're going to compose T to the intersection of the beta 1 boundary of, of this class phi, I guess. Oh, sorry. So let's say this class this has some homology class here. There's some homology class here, and let's call, oops, sorry. Let's see. So let's say that the homology class of the disk homology class is H. Then what we're going to do is the map G will be sort of the intersection of the beta boundary of this homology class H with K, and then so we intersect the sort of beta 0 boundary with K. We count the intersections. That gives us the power of Z. Then we compose with F, and then compose with the power of T given by the beta 1 boundary of the homology class intersected with K. And then this whole thing we're going to multiply by U to the NW of the class. So it looks slightly funny, but that turns out to be sort of the natural way to build these, to define the differential here. And if you define this, if you count polygons in this way, you get kind of an extension of Orzhov and Szabo's theorem. And this turns out to be the sort of natural extension. And it's just that this lambda Lagrangian turns out to be homotopic to the mapping cone of the sum of these two special morphisms. The sum of these two special morphisms. And this turns out to be the analog of this sort of the the Fukaya fact, Fukaya category fact. Let's say of this isomorphism, where you had 3 Lagrangians in the torus like this, and you have the cone of any of them is and we had say the infinity one is the cone of the lambda 1 to the lambda plus 1. And so actually using this sort of isomorphism, you can just, it's a sort of purely local isomorphism, and it lets you define a version of the mapping cone formula basically for any knot in any 3 manifold. I unfortunately haven't had a lot of time to tell you sort of the nature of this isomorphism. Maybe I can tell you for S3 what it looks like. It's actually so there's a long story to this. It gives you, you can think of this as giving you an invariant for 3 manifolds with boundary. And if you compare this to sort of the Lipschitz-Oshva-Thurston description, actually the holomorphic curves in this there are very simple. So I'll tell you just what it is for S3. It's actually basically just, right, I guess actually that'll take a little bit more time than I think I have. I think maybe I'll just explain why one of the elements is a cycle, and then I'll just end there. Maybe so then it sort of seems a little bit more concrete. So, I guess we didn't get to see anything like super fancy here. We didn't get to see any like really cool theorems, but I'll just want to explain maybe why are these guys cycles? And so, it turns out to be sort of surprising because the definition of the differential looks slightly funny, but when you start working with these things, it's quite simple. So let's look at del of theta tau plus phi tau. And the way you count curves is a little counterintuitive, but it actually gives you, it actually is very natural when you work with it for a while. And so there's sort of 2 polygons counted here. There's one here. And so if you think about the recipe for counting curves, that's just going to give us, I'm going to call this intersection point here theta tau minus. This will give you sort of theta tau minus phi tau. And then there's another bygone which sort of wraps around the diagram. Oops, that's not what I wanted. It sort of wraps around the diagram here. It's a little harder to see, but it kind of goes around here, and then it covers this, covers this space twice. So maybe I want to do a little bigger. Right, so it kind of looks like this. And so if you think about how this is defined, well, we have this recipe for doing this, right? So we have one intersection here, we have one intersection here, and we have one W base point. And so we have to think about what morphism we get. Well, you get theta tau minus. And it looks very funny because you think, oh, it covers the base point 1, so you have a U power, and you do. But let's think about what the other sort of terms you get are. So we'll get phi tau. So you have to count things slightly carefully. So what we're actually going to get is a z to the minus 1, right? That's the monodromy on beta 0, and with that power, with the sign of this intersection point, you're going to get z to the minus 1, and then here, this will give us actually a t power. So if you're careful about counting the signs, this is what you get. And this actually looks very scary because we have this z to the minus 1. But if you simplify this term here, what you'll actually see is this is u times t. Now z to the minus 1 actually is going to go to u to the minus 1 times t to the minus 1 phi tau. So kind of, it looks a little scary, but actually you can prove that it sort of always, there's, it looks scary in the sense that like sort of at this intermediate step, you have these negative powers of u, but if we kind of think about this for a second, we just actually can't cancel the negative u powers, and what you get is just this. And so in the end, we actually just get that this is a cycle. So kind of surprisingly, it just turns out to be a cycle. Because kind of what we see is that these 2 terms cancel here. Let's see. So yeah, these 2 terms cancel. These cancel, and so we actually just get that this is equal to 0. The differential of this is equal to 0. So we actually can see these are cycles. I think that's probably all the time I have to talk about it. So yeah, I didn't get time to do all I was hoping to actually do some more examples, but I think that's all the time I have. So thanks for listening to that.
If you wanted to take 3 or 4 more minutes, that's fine. I mean, we generally go an hour. I didn't say. You may have been assuming you were on 50 minutes.
Oh, yeah, I guess I could go a few more minutes. I actually have to go teach at 11, so I should probably let's see. So maybe I'll just say, like, so this diagram actually sort of gives you so this diagram, I don't have too much time, but I'll say this diagram actually gives you the surgery complex of the unknot as well, which is maybe not that impressive, but gives the surgery complex of the unknot, sort of secretly of the unknot, which is maybe not that impressive, but if you compare it to sort of the bordered invariant for the complement of an unknot, the holomorphic curves are very simple. And so I only have a little bit of time, so unfortunately, I can't really explain the sort of the whole picture here. But this A complex turns out to basically be CFK with let's say beta lambda, beta 0, and the B complex actually, if we kind of use this to describe the complex, will be beta lambda, beta 1. And with these local systems, both of these have one intersection point, so it's just a copy of F adjoin W and WZ and F adjoin UT T inverse. And so the map from A to B, well, in Oshroth and Szabo's framework, it's V plus HN. And so V in this sort of new framework is actually going to be the triangle counting map F alpha, beta 0, beta lambda. And we're going to have this not alpha, beta, sorry. Oops, I've just made a bunch of nonsense. So it'll be beta lambda, beta 0, beta 1, and kind of we're going to say input the sigma intersection point, and then the H map is kind of F of beta lambda, beta 0, beta 1, and theta tau will be the input. Let's see, so I can actually sort of draw, there's actually only 2 triangles here. Paste. There's actually only 2 triangles counted here. There's this one here, that is the sigma input, so that's kind of the V generator. And then there's one more which goes all the way around, which is the H map, and that's kind of this triangle here. So there's 2 triangles, one which counts for V and one which counts for H. And so if you kind of think about and then the other comment is like, how does this give you an invariant for arbitrary knots that are not homologically essential? Well, the framing, for example, is encoded in this knot trace, which goes on the Heegaard diagram. So, for example, here, if you wind the knot trace or the snot shadow, this dotted line, you get a different you get a different framing on, you get a different cipher, or a different longitudinal framing, Morse framing of the knot. So unfortunately, I think that's all I can say. I have to go run. I'm a little bit delinquent, so I have to go run to class actually now.
We might have to email a question.